Welcome to The Explainer. Look, I want you to completely shift your mindset today. We're essentially conducting a technical architectural review on a critical yet heavily hidden failure mode in your predictive models. Most developers don't even realize they have this problem until their models are actually deployed, and catastrophic real-world variance just tears them apart. So today, we are breaking down deep survival analysis. It's the exact mathematical framework required to train neural networks when the ultimate outcome in your data is, well, unknown.
Here is our precise schematic for today's briefing. 1. Why standard losses fail. 2. The blindfolded race referee. 3. Understanding the risk set. 4. Cox Partial Likelihood. 5. The log-sum-X optimization. And 6. Deep survival AI applications. Let's get to work.
Section 1. Why standard losses fail.
Standard regression models, they demand absolute certainty. They require a definite target number for every single input. But imagine you're building a predictive maintenance model for, say, an industrial jet engine. If that engine is still running perfectly on the day your study ends, you don't have an exact time of failure. You only possess what we in the field call censored data. You literally only know that the time to failure is strictly greater than the current time. Now, if you discard this data, you're heavily biasing your model to only learn from weak, early failing engines. But if you force the label to just be the current day, your model is going to be catastrophically wrong.
So, the crucial point, the real engineering headache here, is this. How do you calculate gradients and update neural network weights when your training label isn't a fixed value, but an inequality? How do you train an AI to predict a failure time when all you know for sure is that the time is greater than t?
Section 2. The blindfolded race referee.
Okay, imagine you're a referee at a marathon, but you can't actually see the track, and you don't care about the clock. You only have a leaderboard generated by our AI, Speed Coach. This AI looks at runner biometrics and outputs a single relative speed score for every runner. Higher score equals faster runner. Here are your mechanics. A sensor beeps the exact moment a runner crosses the finish line. At that precise second, you check the AI's leaderboard. If the person who just finished had the highest score compared to everyone still running, your AI is performing perfectly. But if the AI ranked someone still out on the track as faster than the person who just finished, you penalize the model.
But what happens to our censored data? What if a runner gets a flat tire at mile 10 and just leaves the race early? Visually, I want you to imagine that runner flickering out of existence on the track, leaving behind only a faint ghost path. We have no idea when they would have finished, so we explicitly ignore them at the finish line calculation. However, and this is key, that ghost path matters. It proves they were faster than anyone who finished before mile 10. They contribute partial, yet highly valuable data right up until the exact moment they vanish.
Section 3. Understanding the risk set. Okay, let's dive into this and map it out. Picture the runners actively moving along our timeline. At hour 2, runner A crosses the finish line. At that exact second, runners B, C, and D are still out on the track. By hour 5, runner C crosses the line, and now only B and D remain. As each runner crosses, that pool of potential finishers dynamically shrinks.
This specific, dynamically updating pool of remaining candidates is formally called the risk set. Now, this isn't just a static matrix of indices in your database. No, it is the exact subset of subjects who are still under observation just before a specific event time. And crucially, it completely excludes those censored runners the moment their ghost path ends. The neural network's only job is to ensure that the person actually having the event has the highest risk score among their specific dynamic risk set.
Section 4. Cox Partial Likelihood.
Back in 1972, statisticians were failing to force messy biological survival times into neat, predefined parametric curves. Then, David Cox published a paper with just a brilliant engineering insight. What if we just don't model the baseline shape of time at all? What if we bypass the absolute time distribution completely and strictly predict the relative risk ratios between subjects?
Now, what's really interesting about this slide is how cleanly it separates things. This is the Cox Partial Likelihood. Look at the numerator. It's the exponentiated AI score of the exact runner who just finished the race. Now look at the denominator. It is the sum of the exponentiated scores of everyone in the risk set. Everyone's still out on the track. If the finisher has the highest score, the numerator is large, the fraction approaches 1, and the loss is near 0. That messy, totally unknown baseline time factor, it completely cancels out in this ratio. It becomes a pure ranking function.
Section 5. The log-sum-X optimization. Here's where the rubber meets the road.
If you process a batch of, say, 10,000 patients and write the math exactly as we just saw, you have a massive problem. For every single event, you have to loop through the entire batch to figure out who is still in the risk set. That is a nested loop, resulting in a catastrophic O(n)² memory bottleneck. On a GPU, this 100 million operation bottleneck will cause an out-of-memory error almost immediately. The engineering fix? Sort the batch by descending time before you even calculate the loss. Because if it's sorted descending, the risk set for any event is simply that patient and everyone below them in the array.
And this brilliantly illustrates the exact one-to-one mapping between the math, summing the exponentiated risk in the risk set, and the GPU optimization. By using that descending sort trick, we can completely replace the O(n)² loop with a single cumulative sum operation, PyTorch's torch.logsumxp. It computes the risk set denominator for all patients simultaneously from the bottom up, dropping the complexity down to O(n) log n. Plus, applying the logsumxp identity mathematically prevents your float32 tensors from hitting NaN errors when you're summing those massive exponentiated risk scores. This right here, this is exactly how you write production-grade survival AI.
Section 6. Deep Survival AI Applications.
Let's move to and see how this builds out across diverse, high-stakes industries. Right now, we're using massive transformers like MedBERT to process sequential electronic health records, extracting the final hidden state into a single Cox risk score. We're feeding vibration waveforms from jet engines into 1D CNNs to predict bearing failure. We're predicting customer churn by pushing demographic embeddings through multi-layer perceptrons. We are even utilizing graph neural networks in drug discovery to pull node embeddings and predict patient survival based on molecular toxicity. Literally any AI dealing with time to event relies on this exact framework.
But I want to leave you with a design challenge for your next system architecture. Standard Cox models assume there is only one way to fail. But what happens to your model when a machine can suffer from an electrical short, a mechanical fracture, or a software fault all at once? Or when a patient can succumb to more than one disease? This pushes us right into the chaotic, highly advanced frontier of competing risks and multitask survival networks. The real world isn't just a single finish line, it's a minefield. Your models need to be engineered to survive it. Thank you for joining this explainer.